Any progressive wave is a function of space and time, so it involves 4 dimensions x, y, z and t. But we cannot visualize 4 dimensions simultaneously. In this video, I have suppressed y-axis in the first slide and animated wave motion using x, z and t. In the second slide, I have suppressed time and using x, y and z for particles at different phases demonstrated the progressive sinusoidal wave.
In this animation, 4 dimensions x, y, z and t, 3 space coordinates x, y and z and the time coordinate t. 4 coordinates are hidden in a single point, just like playing cards hidden in a single point. But as soon as they unveil themselves, just like this, then we can follow any 3 of them, say maximum any 3 of them, x, y, z or x, y, t or any 2 of them x, t, y, t, z, t. But we cannot follow x, y, z and t 4 dimensions simultaneously. So if time is hidden, we cannot see some phenomena. In the next slides, I will show you how, when time axis unveils itself, a beautiful progressive wave is generated, and when it is hidden at the origin, the motion is just like a one-dimensional motion of a particle in a transverse motion. It oscillates along its equilibrium position. So, to unveil the time axis, let us see the next slides. This is a pendulum. This is the suspension fiber of the pendulum. This is the bob of the pendulum. Here, the bob of the pendulum is oscillating along x-axis, and we are considering time axis along the y direction. The direction of the x, y, z axis are shown here. So particle is oscillating along x-axis and time axis is hidden in the equilibrium position. This is the equilibrium position. At this position, time axis is now hidden. If we unveil the time axis, time axis is flowing along y-axis, but the pendulum is oscillating along x-axis about its own equilibrium position. Just like in case of progressive wave, in a pond or in any form, the particles are oscillating about its own equilibrium position. They are not moving from one point to other along time axis in the pond or in any case of progressive wave. But it seems, see this animation, it seems that the particle is following sinusoidal wave. This is actually the projection of the bob of the pendulum which follows the sinusoidal wave, as because x equal to a sin omega t. We have programmed the motion of the pendulum in animation as x equal to a sin omega t. So the projection of the bob of the pendulum follows the sinusoidal wave, but actually the bob is oscillating along x-axis. It is not following sinusoidal path. Just like the particles of the medium of a pond or any medium in case of progressive wave oscillates in its own equilibrium position. Particles are not moved from one point to the other side of the pond. Each particle oscillates in its equilibrium position, say along x-axis. But as soon as time axis unveils itself just like this, then it seems a wave is propagating from one point to the other. In this way, time axis unveils itself. Here it is x equal to a sin omega t, t is along y-axis, and x is the axis along which the pendulum or the particle of the medium is oscillating. So, this is a nice way in which we can depict the time axis Let us stop the motion. The projection of the bob of the pendulum follows the sinusoidal path, as because we have programmed the motion as x equal to a sin omega t in this animation. So let us see again. The particle is following x-axis in its about its equilibrium position. Its to and fro motion is about its own equilibrium position, but along x-axis. It is not moving from one point to other along time axis. In case of progressive wave also, energy transfers from one particle to other in elastic medium, but particles are moving always about its own equilibrium position. They are not moved from one position to the other position of the pond.
A wave is a time varying quantity which is also a function of position. In the previous slide, I have shown how the wave is a time varying quantity. Position is fixed along x-axis. The movement of the particle was restricted along x-axis, that is, it is constrained in the xz plane. In the second case, in this slide, I am considering the wave motion at a given instant of time. This time is fixed. Here I am freezing the time, just like taking a shot at the camera, stopping the animation at a particular time, just like this. Let us stop the animation like this. So it is a sine wave. We can stop the animation at any position at any time, but it is when we are taking a shot at the camera, it is at a particular time. This is the freeze shot at a particular time. Again, this is again a sine wave, but it is at another time. I shall stop the animation at a particular instant of time to get a plot of the displacement of the particle. Each and every particle is oscillating in its own equilibrium position, about its own equilibrium position. They are not moving from one point to other, but the effect is just like a wave, sinusoidal wave in fact. Plot of the displacement of the particles, here the pendulums lying along line of propagation, that is along y-axis. Just like taking a shot at the camera at different times, I am stopping the animation at any time. Every time it depicts a sine wave. Every time it is a sine wave. The phase of the pendulums are changed gradually in the programming of the animation, because in reality particles of the elastic medium oscillates about their equilibrium position just like these pendulums, but different particles are at different positions, so there is a gradual change of phase. Obviously the effect of damping is neglected here.
You can see clearly relative positions of the particles, that is relative position of the pendulum. The relative position of the pendulum creates a sine wave. Thus, if one allows a flow of time axis, not seen here, he or she will see a ripple is moving along y-axis. At different times, wave patterns are different. I have taken so many shots in this discussion. The patterns are different, although sine wave, but they are showing sinusoidal wave. Here every time is fixed. This time is fixed now. This is a t1. Let us again stop the animation at a different time. Say this position. This is another time fixed at t2. But the relative position of the particles, that is pendulum, is forming another wave pattern. There is a ripple is flowing on the pond just like this. Clearly, a transverse wave is moving along y-axis, but the particles, bobs of the pendulum, are oscillating at its own position. Particles of pendulum are not flowing along y-axis. Particles are fixed at their own position. Actually, they are moving along x-axis about their own equilibrium position. They are not flowing along y-axis. Only the energy of the wave is flowing along y-axis in the elastic medium.